Now we're going to be talking about rational exponents. We're going to give a definition of radicals in terms of exponents, and we're going to practice a little bit evaluants, and we're going to practice a little bit evaluating radicals. So, the first thing, a definition, we're going to define the nth root of a to mean a to the 1 over nth power. So now a radical becomes an exponent. As long as or is a real number. Remember that we still have the problems of taking even roots of negative numbers, which give us numbers which are not real. So we're not going to be working with those. Radical defined. If it is a real number, then we're going to say the nth root of a equals a to the exponent 1 over a. And because these of exponents will apply. Okay? So we're going to be able to go back and forth from radicals to exponents and the other way around. When it's convenient, we will, if the other form is more convenient, we will turn to that. And that's a real advantage when we're working with problems. For example, if we take the 16, means that a little 2 is implied as the index of this radical. So by definition, this is going to be considered as 16 to the 1/2 power. On the other hand, if we have, say, 81 to the 1/4 power, we will interpret this to mean that this is the same thing as the 4th root of 81. So if we were to break up 81, and as you know, 83 times 3, so this is 3 times 3 times 3 times 3. So it might, in order to evaluate the 4th root of 81, it might be more convenient to, in order to evaluate 81 to the 1/4, it might be more convenient to look at it as the 4th root of 81, because that says that if 3 factors, therefore the 4th root of 81 equals 3, and by the same token, because that is equal to 81 to the 1/4, 81 to the 1/4 is equal to 3. So you see how nice it is to radicals and exponents. Later on, we're going to see that because we're looking at radicals as exponents, then the properties of exponents are going to apply. Let's do a few more examples. What about the, well, as we said earlier, the 1/3 power is the same thing as the cubic root of negative 27. And we can even make this a little bit easier on ourselves. We can take the negative to the outside because we know that the cubic root of a negative is going to be negative. And so we can just think, what is the cubic root of 27? Well, 3 times 3 times 3 is 27. Therefore, the cubic root of 27, is 3, but we've got that negative on the outside. So now we've been able to see that negative 27 to the 1/3 power is equal to a negative 3. What about if we have a negative 36 equal to the square root of negative 36? No. Because remember, the definition says that the nth root of a number is equal to a to the 1 over n as long as the nth root of a is a real number. And so we simply say negative 36 to the 1/2 is not the same thing as the square root of negative 36 because it is not a real number. And so we'll say this is not a real number. Okay. Now let's look at something else. What if we have the following? What if we have 4 to the 3/2 power? How can we interpret that? It's an exponent, and its denominator's 2, so maybe we can be thinking about this as some form of a square root. But now the nice thing about this is that we can think of this as 4 to the 1/2 power, the whole quantity. With properties of exponents, if we have a base to a power, we multiply the powers. Well, this then allows us to look at 4 to the 1/2 power. The square root of 4 is 2, and therefore we could say this is the same thing as 2 cubed, and that's equal to 8. Okay? But we could also look at this as if it were the following. We could say this is also equal to 4 cubed, the whole thing to the 1/2 power, right? because 3 times 1/2, when we have a base to a power, we multiply the powers. 3 times 1/2 is the same thing as 3/2, so we could cube the number 4 first. Doing that, we end up with 64. So now we have 64 to the 1/2 power, but that's just the square root of 64, and that's the same thing as 8. So you notice that we get exactly the same solution whether we take the root first and then take it to a power, or whether we take it to the power. Okay, we can do this provided that every root is a real number. So now we will do a rule. If we have a to the m over n power, we can interpret this to mean a to the 1 over n power, the whole root of a. But we can do this as long as the nth root of a is defined. Or as long as it is a real number. Again, you have to remember that we can't take even roots of negative numbers, and so that's what we don't want. As long as we don't have that problem, then we could separate it. N equals a to the mth power, the whole thing to the 1 over n. So we could first do the root, as we did over here. This is the same thing as taking the nth root of a to the mth power, right? Or we could say this is a to the mth and then take the nth root of a. Okay, but all of this as a to the 1 over n is a real number, as long as we don't take even roots of negative numbers.